Swayam Prabha. Digital India. Educated India.
So far we have studied the series and parallel combination of different circuit element, which are inductor, resistor and capacitors. So now let us consider the representation of another signals or type of voltage that will be applying. So those falls under the category of sinusoids. Okay. Sinusoids and phasors. So when we talk about sinusoids, so these are nothing but the signal. So sinusoid is a signal that has a form of sine or cosine. Okay. So a sinusoid basically a function that has a form of sine and cosine. And the circuit which are driven by sinusoidal current or voltage are known as the AC circuits, because it is a form of signal where we can see the graphical representation. We have a variation. This is a sinusoids. Okay, so this is omega t. Omega t is the angle, so this will be pi and this will be 2 pi at this point. Okay, and this is the maximum voltage Vm, the peak voltage. This is Vt. So this representation is nothing but Vt as Vm sine omega t. Okay, so this is how the sinusoid is represented. So if these kind of signals in terms of voltage or current source are provided to the circuit, then the circuit is becoming or falling in the category of AC circuits. And we begin with the basic discussion with this thing, and we'll see how these quantities can be represented in another form, which is the phasors. So let us consider this waveform of Vt equal to Vm sine omega t. So in this particular case, the Vm is nothing but the amplitude of the signal, the peak amplitude of signal Vt. So the Vt signal, and Vt is nothing but the instantaneous values. Okay, Vt is nothing but the instantaneous value of signal, or V at time t. Okay, so this also can be represented here. Now another quantity which you can see is new to us, which is omega. It is nothing but angular frequency. Okay, the sinusoids shown in this particular diagram. Okay, so here if you see this duration of 2 pi, okay, this duration of 2 pi is nothing but the omega t. So this is omega t. I'll just write it a capital T and see what are the variation. So where we can write omega t is 2 pi, and the t has a specific meaning here. So this t is nothing but the time period. So this is basically a periodic function which repeats after this instant. So each value which is falling after this 2 pi is a repetition of this cycle. Okay, this positive side and is going to a negative, then again positive. This is AC, alternating. So the time period is basically the minimum interval and the signal duration which repeats itself throughout. So the time period, which is basically in the second, measured in second, and from here omega is nothing but the 2 pi by t or 2 pi f, where f is the frequency of the signal. And frequency is nothing but the number of cycles per second. So it is measured in number of cycles per second and hertz. Okay, so this quantity is measured in hertz. And the unit for omega is measured in radian per second, or simply radian per second. So these are the values which are being measured and the different quantities which are associated with these sinusoids. Now let us look into the some of the other things where we find out that the time period t. So basically Vt plus n of t is nothing but Vt, where n is integer and t is the time period. So this condition is basically the condition of periodicity. Okay, so when this holds, it means that signal is periodic with a time period of t, the capital T. So n is an integer and t is the time period in this particular case. Okay, so now we can represent Vt as in this form also, or we can also write in this just a parameter thing. Similarly, we can write in terms of frequency also. Okay, so this is the representation for the voltage Vt, and these are the terms in which it can be defined. Now there is something which is known as the sinusoids with some phase difference or with some phase. So if I write some other signal in this format, so what is this phi stand for? So here we know all the signals variation, omega is what, Vm is what, it is a sinusoid, and the phi is nothing but phase of sinusoids. Okay, this is a phase of sinusoid. So the total argument, which is nothing but omega t plus phi, this is basically the argument. So argument omega t plus phi is nothing but the argument, okay, with phi as a phase, which is already mentioned. So now examine these two, this one and these two. What is the difference? Okay, so the difference is in the representation where, okay, so let us draw the graphical waveform. So one is this waveform, okay, this one is 1, or I should change the color. So let us try to change the color. Here I'll just put the red color for this. 1 second. What is happening? So basically Wait, we can just pick the red color and now draw the another signal. Why it is not taking this? I'll just select the red color with this thickness. Okay, so now let us see, this is the signal, this is another signal, all the values are Vm. Okay, now this difference is nothing but the phi. Okay, so the difference is phi. Okay, so here if you see, I'll just change here back to the blue color. So the difference, this phi, is nothing but the difference on this. So here if you see pi, and this is 2 pi, here in fact will be pi minus phi. So this basically is the instant where the time period is still the t, basically the 2 pi. Okay, so I'll just write clearly. So this is nothing but the 2 pi, still it is 2 pi. Okay, so this is 2 pi, and similarly here for this signal also it is 2 pi. This for blue, this is for red, this for red signal, or this is for 2, which is this one, and this is for 1, which is this signal. Okay, so these are the two waveforms. Now what we see from here, we see some phase difference. I mean, there are two sinusoids which are shifted, and that shift is nothing but the phase. Okay, so that is the one thing. So here if you draw, suppose this is the axis of cos of omega t, and this is sine of omega t. Okay, normally they take the reference, and you just can take off the any kind of values. So Vm sine omega t will fall here, Vm sine omega t, and here Vm cos omega t. So they are actually having a phase difference of 90 degree, the sine and the cos. So if this phi is 90 degree, so one is represented as cos, and the signal which is passing through the origin 0 is nothing but the sine function of the sinusoid. Okay, so let us now have like one example where we just try to understand. So let us, one sinusoid is given as 12 cos omega t plus some phi. Okay, omega t some phi, where omega is nothing but the 50 and phi is suppose 10 degree. So we have to find the amplitude. Okay, find the amplitude, phase, okay, frequency, and time period. So by looking at this simple sinusoid, so if we compare it with the standard representation, so we can have the Vm is nothing but the amplitude, which is nothing but 12. Then we have a phase, which is phi here. So phi is nothing but the 10. It is a phase. of this sinusoid. Now calculating omega, when given omega is already given as 50, so from here 2 pi by t is nothing but 50, so t can be 2 pi by 50. So 2 pi by 50, if you compute, it will come around okay, approximately. Now if you have to compute the frequency, right, so we have computed the time period. This is nothing but the time period. Now frequency is nothing but 1 by t, so 1 by 0.2 1.26, so this comes around close to 8 hertz. Okay, so this is how the different parameters which are being computed here, and then time period and frequency given omega and phase. So with this understanding, let us now find this sum, or consider the two sinusoids, right? So consider one sinusoid. For example, v1 of t is given as minus 10 cos omega t plus 50. So this is one sinusoid which is given. Then you have another sinusoid which is represented as 12 sine omega t minus 10. This is degrees. Okay, now one sinusoid is given and this is another sinusoid. Now we have to find which sinusoid is leading, or by what angle. So previously we have seen that there's a leading and lagging factor. So the phase difference phi, so if suppose one sinusoid is this one, then another sinusoid is this one, right? So they have some phase difference. So we have to understand for the phase phi, okay, what is happening to the signals with respect to each other, if one is leading or one is lagging. So first we have to convert into standard form where we have this negative term is not there, so that we can write it as this form. If you write both the quantities in terms of sign, then directly phase we can say that reference is common and we can have the difference of phi, and then directly we can calculate. So the first signal is given as v1 of t as nothing but minus 10 cos of omega t plus 50. So this we can write using some trigonometry. Just to take care of this minus sign, we can write it as 10 cos by giving a phase shift of minus 180 degree. Okay, so cos omega t plus 50 minus 180. So negative of cos will be shifted by 180 degree phase. These are degrees. Okay, so the minus sign will be taken care. So this will become nothing but the 10 cos omega t minus 130 degree. Similarly, if you want to write this in the terms of cos, so we can write v2t as 12 cos omega t minus 10 degrees minus 90 degrees. So sine and cos is shifted by 90 degrees. So this will become 12 cos omega t minus 100. So basically the phase of this is minus 130 and the phase of this signal is minus 100. Okay, so we can directly see that the phase difference between v1 and v2 is 30 degrees, correct? So the phi 1, if you represent this as a phi 1, is nothing but a minus 130, and then phi 2, if you see, it is nothing but minus 100. So the difference is minus 130 minus of minus 100 is nothing but minus 30. Or there is a difference of V1 and V2, the phase is having a difference of minus 30 degree. So minus is basically representing the reference. So we are calculating with respect to V1t. Now we can write this or interpret this phase difference is lagging, because minus 30, right, lagging to V2. So basically V1 is lagging V2 by 30 degree, or we can say that V2 leads V1 by 30 degrees. So this is how we can calculate the leading and lagging sinusoids. So the idea is first convert into the same format. Either we can convert into either sine, the both are sine, then directly see the phi 1 and phi 2 and see the difference. Okay, so V2 is leading. We are representing this quantities in a graphical representation. So this is the reference. So suppose this is 180, 90, this is 130. So this is suppose minus 100 and this is minus 130 for reference. So the peak of one signal will be here and the another signal peak will be here. Okay, and it is in the negative direction. So this is basically the V1 and this is basically V2. Okay, so alternatively we have a different component where you can just put them in the sine and cos terms by Cartesian thing. So there are other methods also by which you can leading and lagging sinusoids. So one of the easiest method to do this is phasors. Okay, now let us talk about the phasor. So let us give the heading of phasors. So phasor is nothing but a representation of a sinusoid in terms of complex numbers. Okay, so phasor is the representation of sinusoids in complex numbers. Okay, so phasor is the representation of sinusoids in complex number. So we know that what is a complex number, where Z is the complex number so this is basically the Cartesian form, and x and y are the real values. So x is the real component and y is imaginary component. Okay, so these are the two components. So if you want to represent a real number, like this is the representation of Z and this is the real axis and this is the imaginary axis, so y will be here and x will be here, and this is nothing but the Z. So magnitude of Z is nothing but x square plus y square of whole root. So 10 inverse y by x is nothing but 5. So this is the representation in the Cartesian form. So this is rectangular form or Cartesian form. So another one is known as the polar form. So we have a polar form. So polar form, the z, the same number will be represented as r angle phi, or exponential representation is this one. So what is the r here? So this is nothing but the polar form, and this is nothing but the complex, or it is known as exponential form of the number z, which is a complex number. So now if you want to see the r is nothing but the modulus of z, which is x square plus y square of root, and then the total magnitude of r, right? So r, if you want to see the x in terms of the r, then x will be r cos of phi, and y is nothing but r sin of phi. So from here you can see, so the mod z is nothing but the r, so the z cos phi, okay, is x. So this is basically r cos phi. So this projection will be cos phi, and this projection will be sin of phi. So if we can write this in the different form, so this z may be written as x plus j of y, or I of y. We should not get confused with the I current. So if you remember, this is a complex number, which is basically the z, x plus iy. I stands for iota, not the current here. Or let us assume that this is x plus iy. Consider is j, because we'll be going to the representation in the circuit, so don't get confused with the current. So r plus jy. Here also we have written j correct, that is fine then. So now this can be written as r cos of phi plus j sin of phi. So this is nothing but the r cos phi x, and r sin phi is y. So this is j. Sorry for this. So this is j. Okay. So if you see recalling the some property z1 plus z2, if two variables z1 and z2 are the two complex numbers, then z1 and plus z2 is nothing but so real number will be added, real component will be added together, and if you want z1 minus z2, then we have real component subsection plus imaginary component of. So now if we see multiplications, so this is addition, this is subtraction. Now multiplication, if you see, so we can write z1 z2, right? So it will be easy if you use polar form. So r1 r2 angle will add up, phi 1 plus phi 2, and z1 minus z2, this will be r1 by r2, and angle will be phi 1 minus phi 2. If you want square root of z, okay, so this is nothing but, these are different properties. Just to recall, I just wanted to show you. So this is nothing but root of r, and angle will just go half. Okay, so this is the root z, and the complex conjugate z star, which represent the complex conjugate, is nothing but the x minus iy, j of y, where so these are basically the representation in the phasor terms or complex numbers. Now let us relate the sinusoids and phasors now. So the sinusoids, okay, so let us remove this line, make it on the close to center part. So we have some rotating vector Vm whose magnitude is Vm and the angle is phi. Now if it is rotating, so at this instant the projection on the cos will be high, sin it will be 0. Suppose this is phi here, this angle, this is the value. If it reaches this point, this will be value, it will go to the maximum and then it will start reducing, and this is how the projection of the points will come. This basically forms a sinusoid. So here it is basically a rotating vector, it is just rotating with the speed of omega, the angular speed, correct? So this is how it is represented. So suppose this is here, now the phi became 90 plus alpha. Suppose this is alpha from this axis, so this is 90 plus alpha, so 90 is here, this is pi by 2 and alpha is little further, so this point is nothing but this goes directly here, it projects here. Okay, so the projection of all these rotation points is nothing but the sinusoids. So suppose we have a sinusoid Vt as Vm sin of omega t, then we can write it as Vm angle of phi. Okay, so these are the quantities. Now in terms of phasor, if you want to represent the real axis and the imaginary axis, so you have V, the voltage and the current. So suppose this is real axis and this is imaginary axis. Okay, now you have one phasor of the voltage and one phasor for the current. The voltage is having angle of phi and the current is having the angle of theta with respect to the positive real axis, and this is Vm and this is Im. Now how do you see this? So with respect to this, in the direction, if you see omega, it is rotating here, so omega is anti-clockwise, so the phi is leading angle. Okay, the phi is leading angle and theta, which is downward to the real axis, so basically it is negative, so it is lagging angle. So we will be writing the phasor Vm. So this phasor will nothing but the Vm angle theta, and this phasor is nothing but Im angle minus of, sorry, this is phi, right? This is representation of phi. This is phi and this is minus theta. So this is how we are going to represent, and the phase difference between Vm and V2 is nothing but phi minus of minus theta to phi plus theta. So total phase difference is between V and I is, or Vm and Im is what? Phi plus theta. So this is a total phase difference. So this is the phasor which is being represented. Now suppose there is another quantity. So for example, we consider like Vm cos omega t plus phi. So write it as, very interestingly, we have seen this Vm angle of phi, correct? Now if we have Vm cos omega t. Okay, now Vm cos omega t plus phi. Vm cos, sorry, this we will change the sinusoid to sine. Now this is sine. So Vm sin omega t you will write as Vm phi minus 90, or the 90-degree phase shift will appear. Okay. So this phase difference will depend upon the what type of sinusoid we are comparing. So this will be useful when you want to have a difference of, you know, the two different phases, or the phasors you want to compare which one is leading and which one is not leading. So that time we'll just compare the same form of sinusoid either in sine or cos term, and then we'll see what is the phase difference. So this is how the phasors will be treated. So the derivative Vt transform into the phasor domain. So we will just okay, so what we'll do, we'll just take a derivative of this. Okay, so suppose this is one equation and we want to derivative d of Vt by dt. So what we'll get? We'll get nothing but omega Vm sin will become cos of omega t, correct? So this is nothing but omega Vm j times, right? Sorry. So this will become nothing but omega Vm cos of omega t. Now you want to compare with this, right? So we'll have to provide a phase shift, omega Vm sine of omega t plus phi, which will be like 90-degree. So in this particular case, we can just write this d v of t by dt. This phi is nothing but the e into j phi, correct? So this will become the real part of j times of omega Vt. So this is the phasor derivative. So basically the d by dt will transform into j omega. You can just derivative the take a derivative of this time based signal and then convert it to the phasor derivative, which will result the quantity d by dt as a j omega multiplication. Similarly, if you integrate, so if you want to integrate, you will see that some quantity v dt, it will be nothing but integration by j omega. So it goes, integration goes 1 by j omega, and the differentiation with respect to time goes multiplication of j omega. So this will be very useful. So now, for example, consider the two phasor or the complex number. Okay, so now you consider the two complex numbers, suppose 40 angle 50 degree plus 20 angle minus 30 degree. Now you have to add. Okay, these are the two numbers, z1 and z2. So where z1 is nothing but 40 angle 50 degrees, and you write z2 here, 20 angle minus 30. So whenever we are adding the two numbers, the real and imaginary components will add up together, right? So convert it into, this is nothing but the polar form, r angle phi. in the form of this. So if we want to see, so this will be like R, here is 40 and phi here is 50. So this can be represented as 40 into cos of this 50, phi is nothing but 50 plus j times of sine of, sorry, not phi, the 50, okay, sine of 50. Similarly, the Z2 will become 20 cos of minus 30 plus j of sine of minus 30. Okay, so this is the representation. Now you can add together, so where we can see that the we can see Z1 plus Z2 nothing but 40 cos of 50 degree plus 20 cos of minus 30. This is the real component plus j times of 40 sine of 50 degree plus 20 times of sine of minus 30 degree. So if you do this thing, the Z1 and Z2 will come, so it will come around 43.03 plus j of 20.64. And if you convert into the polar form, so this is nothing but the rectangular form. So the question was asked in the values are given in the polar form, so the answer in the polar form should be 47.72 and angle of 25.63. so this is the phase angle representation. So the phase of this, so suppose you want to represent this, so this is real axis, this is imaginary axis, this is Z, which is nothing but the Z1 plus Z2, and the mod of Z is here 47.72. this is the length of this Z, and this angle is 25.63. so this is how you represent the phasors. Okay, so these are the phasor representation, the basic understanding. So now we'll be using this technique for utilizing in AC circuit most of the time. So we'll just, for the sake of understanding, we have covered this topic now. So in the later stage, when we'll be using the AC circuits, that time we'll see that how this method can be used to solve these sinusoids, or the calculation can be made easier. So with that, let us close this phasor point and we'll start with the